Okay, so we are returning back to the human and human biomonitoring. I am going to talk about the applications of the comet assay in human biomonitoring with an emphasis on effect of cell types and effect of cryopreservation. I think you have already heard some stuff about human biomonitoring, but I will just quickly sum up. Human biomonitoring, of course, a great tool to monitor the effect of environment on human health. And as you can see here, we expose daily maybe several or hundreds of substances via air, soil, or water, and especially via our nutrition, via food. And we came in contact with several products, from the cosmetics, toothpaste, toothbrush, to the utensils that we use for cooking, maybe like pans, or even the furniture that we use or the clothing. And we expose via various routes like ingestion, inhalation, or skin contact, and we can actually do the risk assessment or monitor the effect of the substances and internal exposure by using biomonitoring. And for this, we can use various samples like some biological fluids, blood, urine, or even buccal cells, or hair, or nails even. So actually, human biomonitoring is commonly used in occupational settings to measure the conditions of the workers. However, recently it has been used increasingly for monitoring human health and assessing the disease risk. It provides a good information about the exposure and clarifies actually the relationship between an internal dose and possible risk between the disease prevalence. So we can assess the environmental exposure, but as well as its biological impact. So as you can imagine, DNA damage and also the DNA repair can be important health factors. So it can be measured by comet assay. As you already heard, comet assay is a versatile method. It can use in various different modified versions. It allows us to measure DNA damage, but also the DNA repair. And it might be a useful biomarker for predicting the disease risk, especially if you consider cancer risk. So after exposure, we can have DNA damage. So as we learned already, that DNA damage can be repaired. But if the repair is not efficient, we can have error and we can have mutations, or sometimes repair rate is so low that it's not repaired, if either incorrectly repaired or not repaired, and it can lead to mutations, which can initiate the carcinogenesis. So with this, we have in the decades, 10 to 30 years, maybe the cancer is manifested as a result of the exposure. However, we can maybe use the DNA damage and repair as an early predictor marker before this 10, 30 years occurs. Comet assay offering a good approach for us because it's easy, quick, and we can use comet assay for this. However, we need to establish the predictive power of comet assay by using cohort studies to see what kind of matrix we can use. And if you can imagine as human biomonitoring, we have huge sample sizes whether we can work with cryopreserved samples. So there are a lot of case studies actually which shows two groups, like a disease group and a healthy group. There is a comparison between comet assay and DNA damage or repair levels. However, there are not enough studies, retrospective studies, which can help us to guess the predictive power of comet assay. For this would be the best approach actually to using biobank samples, because we have health records and we have a huge sample which collected over decades, so we can compare the predictive power of comet assay with comparing in individuals DNA damage and repair levels at the early level and see after 10 years, 30 years later, what kind of disease the individuals get, how is the level of DNA damage or repair now. But as you can imagine, for this, we need to use cryopreserved samples because biobanks have stored samples over decades, so they are cryopreserved. But what else we need to use cryopreserved samples? If you're working with a joint project from several different locations that you have to collect samples, you again need to freeze samples to gather all the samples together and analyze them. And if you are working with a big sample size, of course, you need again maybe run all the samples at the same time to reduce the day-to-day variations. Then you again need to use cryopreserved samples. And if you have a retrospective study that you want to conduct a long-term observation, as in the cancerous case that you have an early collection and you want to see after 30 years whether that individual get a disease or cancer, and you again need to collect the samples over decades time, that you need again cryopreserved samples, or using long-term samples from biobanks for the same reason. However, we have some issues due to the cryopreservation. We can have increased background damage because of freezing and thawing cycles. You might know this already from the cell lines if you are working with cell culture. So when you thaw the cells, it takes some time until they recover and you can do the experiment. So that means we need a freezing medium that you also probably know this from the cell culture, that freezing medium might also affect if you're doing an enzyme activity assay and you have a lot of cryoprotectant, it can also affect your assay outcome. So, and when you have thawed the cells and cultured the cells, it might lead to a certain population of the cells will die out, and you have a selection procedure due to that because you lose some cells. And of course, it's a facility question actually, because keeping long-term stored samples, you need liquid nitrogen, you need -80 or 70 meanwhile to save the electricity. However, it should be stable. So you need, it can also time to time occur that you have a freezer malfunction and you lose your samples. So it's also not so easy on that sense. What are the important factors if you want to work with the cryopreserved samples? First of all, storage of a suitable material in a suitable way. So you have to find a correct storage way, and you have to choose a correct matrix that you can work with. And using methodological controls, Amaya already mentioned, it's very important, comet assay, that you have somehow to monitor day-to-day variations. Also, whether the assay works as expected, you need to use methodological controls. And during the collection of samples, bench time and shipping, if you have a multi-central study, can affect the results, as well as after thawing. If you have one sample laying longer than the other one, it can also affect. So you have to optimize actually the collection conditions, bench time, and if it's shipped under what condition it needs to be shipped has to be also considered. And finally, stability of DNA damage in cryopreserved sample over time is a question. So if you are having the samples decades long, you have to understand what is the effect of this long time storage on quality of your analysis. So we tried to answer some of this question experimentally. So we could collect some data and develop a better understanding, but of course we couldn't answer all these questions fully yet. I would like to remind you a small overview. You have already seen there are a lot of versions of the comet assay. In the results that I'm going to share, I will share with you mostly the alkaline comet assay that you already heard about. It can detect single and double strand breaks and alkali labyl sites. And I also conducted FPG comet assay, so for detecting of oxidized DNA lesions. And I will also share a repair comet assay with you, but it's a bit different repair comet assay than Sabine's share, so I will try to explain you quickly what is the differences. So as you can imagine, human biomonitoring, one of the most commonly used sample is a whole blood sample. It can be used as it is. And in the biobanks, most common stored sample type is Buffy code, because you can spin the sample quickly and you get the plasma, you get the erythrocytes, and then you get concentrated white blood cells, leukocyte, that you can use for different aims. So they do it by this way because mostly they are aiming to isolate DNA, and in plasma they have some other biomarkers, so they store mostly the Buffy codes. Of course, for comet assay, we need some cells with DNA content, so we need the white blood cells that we can use in comet assay. Another possibility that you can do a density gradient isolation. So you have a density gradient, you spin them, lay them blood samples on the density gradient, spin them down. You have again the plasma. You have peripheral blood mononuclear cells. After the density gradient below it, you have the erythrocytes. So you can use all these three different sample preparations, whole blood, Buffy codes, and PBMCs in comet assay for analyzing DNA damage or repair. But what are the differences we will see now? So we had a comparison from 10 healthy individuals that we measured in these three different blood preparations, basal DNA damage, and we did the FPG sensitive site measurement by using FPG comet assay, as well as we conducted an ex vivo H2O2 challenge. So that means after embedding the cells in agarose, you can apply them, you can treat them with H2O2. To induce an oxidative stress. And if the cells have more antioxidant capacity, maybe they are reacting less sensitive to H2O2 challenge or more. So then you can see the individual reaction to this challenge. And also maybe it's an indirect measure of antioxidant capacity of the cells. So what we see here you have them in whole blood, Buffy code, and PBMCs. So in the basal DNA damage, DNA strand breaks in between whole blood and Buffy code and PBMCs doesn't differ much. So we can use all the three samples for measuring this. PBMCs have slightly but significantly higher level of DNA in the tail compared to the whole blood and buffy coat. However, they can all use for the same looks from this graphic. H2O2 challenge is although a bit different in whole blood and buffy coat, we have no reactions, whereas the PBMCs showed a good reaction after H2O2 treatment. So that means if you want to induce a damage by an ex vivo challenge, whole blood or buffy coat might not be the best samples. And this kind of challenge is mostly done in nutritional studies to see the antioxidant activity maybe, and that means you will need PBMCs or you have to get white blood cells from the buffy coat or whole blood with additional washing steps, which is also possible but not well optimized yet. Another possibility that we did, FPG sensitive sites. So we measure actually with the buffer and FPG treatment, and this is what you see here, the net FPG sensitive sites. So oxidized DNA lesions, and we can measure it in whole blood, buffy coat, and PBMCs. There is no difference. That means you can do the alkaline comet assay and FPG comet assay in this all three different blood preparations. However, for the ex vivo H2O2 challenge, you should use rather the PBMCs. What we wanted to see next, whether we can use all these three different blood preparations also as cryopreserved. Is there any difference between the fresh and the cryopreserved version? So again, from the 10 individuals, we have the whole blood, buffy coat, and PBMCs, which were freshly done. And also after freezing, we told them up to a year storage. We don't have here decades-long storage, it's up to a year storage. And we conducted the comet assay. What we have here that you can see, we have no difference between the fresh and cryopreserved samples in any of these blood preparations. Basically, up to a year, we didn't see any increase in the basal DNA damage, and we could use all these three blood samples. What is a clear difference in the storage? Whole blood and buffy coat were stored without any cryoprotectant, so which is very practical. So when you get the samples, you have the whole blood, you can just do a small aliquots, has to be in small portions, and then you can freeze it and use it. Buffy coat, you have to spin down the samples, collect the buffy coat layer, which is concentrated with the white blood cells, but you can also freeze it in a small portion without a cryoprotectant. And PBMCs, you need to use a cryoprotectant medium after the isolation. That's the difference, maybe. Time matters. So look closer, what is the composition of the blood and what are the differences among these three different blood preparations? So we have the whole blood. We can spin it down and we have concentrated white blood cells, leukocytes, that we have neutrophils, eosinophils, basonophils, monocytes, lymphocytes, also some platelets and erythrocytes in the buffy coat. And if we layer it on a density gradient medium and do the spin down to isolate the peripheral blood mononuclear cells, then we have lymphocytes and monocytes that we collect and work. And polymorphonuclear cells like neutrophils, they are in the lower layer together with the erythrocytes. So they are not in our comet assay samples anymore. So look, what are the advantages? If you work with the whole blood, actually, you can work with a small amount of blood. You can even work with a finger prick. So you can get the blood samples with a finger pricks, which is also very useful maybe. It's less time consuming. You get the samples immediately and you can work immediately. And cryopreservation is not necessary. So if you have a small amount that you can freeze and you can thaw later on, so you don't need to do much. It's quite quick and simple, especially if you are working with a big clinic that the nurses doesn't have any time to isolate the cells for you, and you can ask them do a small portion of a whole blood and freeze it, and you later collect the samples if it's another city or so on, which is very practical. For the buffy coat, we have only concentrated layer of leukocytes here, which are concentrated white blood cells. We have all the mononuclear cells and polymorphonuclear cells. It's the most common type used in biobanks. That's why we were interested in this samples also, which is also quicker than isolating PBMCs. However, a bit more time consuming compared to the whole blood, but still is easier. With the PBMCs, we have a more uniform population of the cells, which is a good thing that we have only mononuclear cells. And these cells are the cell types have actually the longer lifespan among all these cells. So for the exposure studies, it might be a good and representative because they are longest in the blood circulating all over the body. They expose maybe longer time compared to the polymorphonuclear cells. Sometimes they only there for 24 hours or up to 3 days, which might be also a good thing to know. So what we also wanted to see after that, so we can count on that, we can analyze the FVG comet assay and alkaline comet assay data with the fresh and cryopreserved samples. And if we have PBMCs, we can even do the ex vivo H2O2 challenge, and it looks like positive. What about the DNA repair activity? At that time, what we wanted to do, we wanted to use the cells in culture, like intact cells, not preparing the protein lysate, as Sabine explained. However, using an alternative method with acetylcholine block DNA repair activity assay. So what we have here, we have the blood cells. We have here only PBMCs because we wanted to culture them. So after isolating, and we have a substance treatment, that's why also we choose the PBMCs. So after isolating, you treat them with a substance or not treat them. So we use here UVC, which can induce bulky adducts. And then you can do after treatment directly comet assay, or you give them time to repair with an inhibitor or without an inhibitor. So you put them, time point 2 is like the 2 hours later. So what you have here, you have them in the incubator at 37 degrees. Normally, bulky adducts are not strand breaks, but when you start repairing it, the repair enzymes, you can create strand breaks if you don't do the gap filling. So the repair is have first the recognition of the lesion, and the enzymes cuts the lesion out. That means you create a strand breaks, and the next step will be the gap filling. We inhibit the gap filling with the acetylcholine. It's a DNA polymerase inhibitor that you can add up. That means the gap filling won't take place, and the strand breaks will accumulate over time, which will show us the incision activity of the repair enzymes. So you can see here in the 0 point after directly treatment in control, the background level, acetylcholine doesn't do any damage by itself, and we have 5 joule per quadrat meter UVC. That doesn't do anything alone. We also don't expect it in that doses because it doesn't do strand break induction. And with the combination of inhibitor, we also don't see much. However, after 2 hours incubation, you see here a slight increase without an inhibitor because there is an incision and the excision going on at the same time. However, once we give the acetylcholine to inhibit the gap filling, these strand breaks are accumulating over time, which shows the incision activity of repair enzymes. So the UVC-induced lesions are repaired, so it can be counted as a repair activity. One of the versions of repair comet assay, which is done in fresh samples. We did the same thing after cryopreserved samples. So we had the cryopreserved PBMCs. We thawed them, washed the freezing medium, and then we put them in culture. First one we treat directly and do the comet assay directly, and the other ones we give repair times 2 hours at 37 degrees with or without acetylcholine and conduct the comet assay. What you can see here, the basal damage, when you don't put them in culture, there is no difference. So we can directly thaw them, treat them, and use them in comet assay. But when we leave them on 37 degrees for 2 hours, we have increase in background damage already in control. That means the background damage is increasing, and we cannot observe any repair activity because it's masking any activity. So we have basically elevated DNA damage due to the freezing, thawing, and culturing at 37 degrees within 2 hours, which looks like that this kind of repair assay might not be possible to conduct with these cells. But we have it as next, actually, after thawing them, we cultured over time to see how is it going. So we have here fresh in black and gray color is the frozen samples from 6 different individuals. These are PBMC samples again. You see at the directly after freezing and thawing, you don't see much difference at the 0 point. So you can use it. There is no increased basal DNA damage. Within 1 hour already, frozen samples showing like a double increase in the DNA damage. Within 2 hours, it's even higher. And if we wait overnight, so we have again low level of DNA damage, or it came back to the normal control level. And this is because we lose 25% of the cells. So here, the cells with having increased DNA damage dies, and then you have again lower DNA damage in 16 hours. That means I could do the repair assay after culturing cells overnight, and next day I could treat them for this kind of repair assay. However, I lose a certain population of the cells, and I cannot say what would be the effect of this population on my outcome. So there is a kind of a selection procedure. But that would you also expect probably when you freeze and thaw the normal cell lines, you put them in culture, and next day you'll be a bit less cells because some of them, because of freezing thawing, will die out, and then they will start proliferating again. Then you can use them in 2 weeks maybe for your treatments. When we look the distribution of the DNA damage in cryopreserved samples, you can see very clearly. So at 0 point, after directly thawing, most of the cells are like having lower than 5% DNA in the tail, and some is in 10 and 20%, and higher levels you don't almost see any cells. Within 1 hour, you see the cells with the lower than 5% DNA damage is like actually going down, and in 2 hours too. And you have already increasing categories in like more than 20-30% damage. So that means a small population of the cells having a higher DNA damage, which is affecting our average DNA damage levels. After 16 hours, you see again most of the cells are having lower than 5% DNA in the tail, and we don't see any in black color in the categories more than 30% DNA damage, because cells are died overnight, and then you have again the cells, the fit cells, kind of a selection procedures goes on. The highly damaged cells getting eliminated. Yes. We did one time, and then we didn't see much big difference, so we decided to do overnight. So we did like 4 and 6 hours, and certain time points are not so attractive for students because of the working hours. So it didn't show a big difference. So we thought we keep the 1 and 2 hour, and there is another reason for it, because the repair assay we did here, we use UVC and we use H2O2. H2O2 is mostly repaired in the repair kinetic within an hour. And UVC, we see the most repair activity within 2 hours. So we wanted to keep these 2 points. And we wanted to show the overnight, because the overnight, again, it's going down. And 16 hours because we had a stimulation, and without stimulation, like inducing the proliferation of the lymphocytes. And after up to 16 hours, it's okay, but longer than 16 hours stimulation can affect the DNA repair activity again. Okay, after seeing this, we are going to analyze now decades-long samples. So we wanted to analyze, actually prepare some assay controls. As the assay controls, what we use cryopreserved TK6 cells. We treated them either with like a solvent control, was the water in this case, or with the potassium bromide in 2 millimolar, because we wanted to use them as the assay controls in FPG comet assay. So we need to induce oxidized DNA lesions, and we freeze them as aliquots. So as you can see, after thawing, so it's in the buffer control and FPG. So we could have acceptable day-to-day variations, and we could use them as positive control, these cryopreserved TK6 cells. We don't have any abnormal results. So we decided to freeze a lot of aliquots and run in each experiment also frozen assay controls. What we also tried, we thought if we receive samples from biobanks, so they will be shipped on the way, they can get thawed on the way. What is the best way of shipping? Should they ship it in like a fridge temperature after thawing, or it can be used, because I had a lot of samples, they were already readily thawed and frozen again. It might make nothing for DNA isolation, but we wanted to see also, can we use it for comet assay? So that's why we did like a small experiment. We used them directly after thawing, number 1. So that is the average damage. We thawed them and lay on 2 hours ice, because if you are working with huge amount of samples, I know 100, 200 samples, it might also take time until you can pipette all the samples. So we wanted to see how is it like storing on the ice during pipetting procedure. So you see already you have an increasing background damage if it's waiting too long on ice. And what we did, we kept them 36 hours at 4 degrees after thawing to see whether you can keep them in a cold temperature. So you see a lot of increase in the background damage, so we cannot keep them. We thawed them quickly and freeze back and rethaw them. You see again increased damage. So basically, we cannot use already thawed samples. We cannot ship them at 4 degrees. We cannot keep them long time on ice, so they have to be frozen and kept in minus 80 degrees or liquid nitrogen, even better, before we can get and analyze them. After that, to see whether we can really analyze decades-old samples, cryopreserved sample, we had a collaboration with the German Cancer Research Center in Heidelberg. So they had a European prospective investigation in the cancer and nutrition study. It's called, in short, EPIC study. It's one of the largest cohort studies in the world with more than 500,000 participants, and they recruit across 10 European countries, and this people also followed almost 15 years long. And by now, number of the cancer cases might be developed in the EPIC cohort is more than 100,000 individuals. So we had the samples from the German Cancer Research Center in Heidelberg. They are a part of the EPIC study, and they had about 25,000 participants. We had some limitations because they had available samples as buffy coat preparations in straws and cryotubes from the beginning point of recruitment and the follow-up points. And from the further follow-up points, they had also isolated PBMCs, but not at the baseline at the recruitment. So we have a limitation in the sample type. What we got the samples, the baseline samples are between 1994 and 1998 collected. And then they had a first follow-up time point 1, 2010, 2011. So it's like almost 14 years apart. And the time point 2 is a 1 year apart from the follow-up point time 1. So we had 50 samples from buffy coats, and we had 99 samples from PBMCs. One got kind of lost. It's supposed to be 100. One got forgotten, I think. So that's why it's 99. So what we did, we run the comet assay with all the samples at the same day and parallel time with PBMCs, also the buffy coats. And as you can see here, you can see the correlation between the DNA in tail percentage in baseline. So it's from 1994 to time point, follow-up time point 1 after 14 years, almost apart. So in buffy coat, we see a moderate or weak positive correlation. So the 2 time points from the same individual doesn't show a good correlation in buffy coat samples. In PBMCs, we had only the follow-up time points. So we have the T1 and T2, which are 1 year apart. So we have time point 1 here, you can see in the x-axis, and time point 2 in the y-axis. So we see a moderate positive correlation. So correlation coefficient is much better here. But it's quite hard to explain what kind of factors can play a role here. So what we also did to see, because we got the healthy individuals as a test run from the EPIC, so we mixed our own collection from morbidly obese subjects, which were PBMCs, frozen, cryopreserved frozen PBMCs, in this collection, and we run at the same time to see whether we can detect a diseased person compared to the healthy person with using cryopreserved samples. What you see here, we could see that BMI 30 and above show significantly higher FPG sensitive size. So we have done FPG comet assay and analyzed the oxidized DNA damage here, significantly higher above BMI 30 in this group. So comet assay with PBMCs, we could determine the healthy group, differentiate between the healthy group and disease group. And you see here the correlation between BMI levels, because we could cover a broad range of BMI from the normal to the morbidly obese, so from 20s to 50s. And we can see here the FPG sensitive size on the y-axis that you see it does not differentiate from the linear. So we have with increasing BMI levels, we have increasing DNA damage, which can mean that if you are a obese subject that you lose weight, every weight that you lose, you can profit from it because it can contribute to reduction of your DNA damage, which can be linked to Sabine's results on the repair activity, maybe, if you consider it. So to sum up the all stuff together, cryopreserved samples are actually suitable for determining DNA damage. Long-term stored biobank samples also can be used, but we have to think about what sample times, what blood preparations is the ideal for us. And DNA damage from PBMCs actually show a good consistency over a time for an individual. They are looking promising. For buffy coat, I think we need to work on further to understand the limitations and why the results looking like this. But there are important factors we still need to consider. Bench time, composition of the freezing medium is important. Storage conditions can affect all the outcome. So whether it's in liquid nitrogen, it is -80. Whether your -80 is fluctuating. When you ship the samples, what is the temperature fluctuations in this during this time? We need the good methodological controls, and frozen cell lines can be useful for this aim. It's necessary to control the stability over extended time period. So if you have frozen. Even the TK6 lines, you can control them, like covering at certain time points to monitor the stability of DNA damage over time. And what is important, if you are going to culture those cells, you need to understand that you might lose a certain population of cells during this culture, and you might need to consider the effect of this, because we don't know what kind of cells dying out, which are the highly damaged cells, whether it's a sign for the fitness of the cells. So it might affect your outcome if you want to culture them.